Hopefully you just did a handful of problems, or recently did a handful of problems, one of which should have been this one right here. And I wanted you to try to figure out what went wrong with our method. Well, as you can see, I get r squared plus 1 is 0. I didn't show that work, but you should have gotten there. Should have gotten r squared plus 1 is 0. Give me r squared equals negative 1. But then when I have to square root it, I get plus or minus I, or plus or minus root negative 1, which is plus or minus I. This is really like the first time in your careers as mathematicians that you have had an imaginary number show up and you're like, oh no, I have to use this. And we are going to use it, and you will become extensively familiar with imaginary numbers and what to do with them. Before we do that, I want to try to intuitively solve this equation. To do that, I'm going to write it a little bit differently. I'm going to write x double prime is negative x. Now let's think about this. This says start with a function, derive twice, and then get back the negative version of the original function. So the question is, what you know, and if I say it, you'll be like, oh yeah, you know two functions, in fact, that do that. Derive them twice, they come back to themselves, but the negative version. Hopefully you're seeing it. If I take sine x, I don't want to use x's, I want to use t's. If I take sine t and derive it once with respect to t, actually maybe I should use some better notation, d dt it, then I get cosine t. If I dt that again, I get negative sine t. So notice it is the negative version of the original function. So that means it fits this thing. Same thing with cosine. Derive it twice. We get negative cosine t. So the question is, what does that have to do with this and the equations that we had with e to this, right? Because remember, you would do c1 e to the, I'll call it r1 t plus c2 e to the r2 t. So how does that translate to sines and cosines? This seems impossible. But you know what? It's not. It's totally, fully real. Well, real, complex, real. Get it? Anyway, and it comes back to your absolute favorite, you hear me pounding the table? Favorite things in the world. Taylor series. No, I'm not going to ask you to do all the Taylor series work that we did, back in BC. Don't worry about that. This is not, we're not going to go down that hole, right? There are only 3 Taylor series that I care about, and they are the 3 in front of us right here. And I actually think that you will see that it's pretty magical. What I need to do is let's go back to this thing. So I'll do it in green. Said I need to do x of t, the solution to this thing. Well, if I just follow the logic from the earlier ones, I get x of t equals c1 e to the it plus c2 e to the negative it, where I is what it is, which is root negative 1. So the question is, how do I do that? Well, this is absolutely magical. And maybe this is a side step from this problem, because I have to work out a formula. This is called Euler's, not Euler, formula. I don't know. It could be the most powerful and consequential formula in math and engineering. There's like literally books written about just this formula. And you can do so many things with it. What it does is it takes imaginary numbers and turns them into things that we can actually work with. And it goes way beyond just use in differential equations. It's so ridiculously useful. From our perspective, we use it whenever we get these imaginary roots. And I sort of said this maybe somewhere along the line, but we keep coming back to it. We keep coming back to different styles of solutions, and we keep using Euler's formula. So Euler's formula, I'm going to write it, and then I'm going to show you why it's true. Euler's formula says, let me pause. Okay, so it says e to the iat equals cosine of a t plus I sine of a t. So what it does is it takes an exponential and turns it into sines and cosines. That seems kind of wild. Also, it's taking the exponential of an imaginary number times time. So what I'm going to do is work out an easier form of this. I am going to work out, what do I want to do it in? Yeah. I'm going to work out e to the it, and then I think that you should see where if we were to throw an a in there, that it would give me what we have over here. So, want to do e to the it. How do I do it? Well, I don't know how to do it, right? But I do know that I can expand an exponential like this. Notice this is e to the x. Everywhere there's an x here, right? I can do e to the by replacing all of these thes right there, right? So if I replace all those little underlined x's with it's, then I'm using this Taylor series expansion to rewrite e to the it. So e to the it is equal to, all right, 1 plus I times t plus, I'm going to write it as I squared t squared, right? Because that would be it squared, which would be it, and then I could reorder it and turn it into this, over 2 factorial plus I cubed, I don't like that, I cubed, t cubed, over 3 factorial plus, I'm going to write a handful of them here, I to the 4th, t to the 4th, over 4 factorial plus I to the 5th, t to the 5th, over 5 factorial, plus we'll do one more, I to the 6th, t to the 6th, over 6 factorial. Now, before I go any further, what I want you to see, and you should have noticed this back, and I tried to point it out to you when we did Taylor series in BC, but the sine expansion here and the cosine expansion here, look, this is all the odds. This is all the evens. It seems like if I could add all the sine expansion pieces with all the cosine expansion pieces, but somehow get rid of all of these alternating negatives, that I would wind up with an exponential, right? So I want you to start seeing it before it comes up. We have different powers of I. So I'm going to do some scratch work over on the side. I. Well, that is just I. Next, I squared. Well, that's root negative 1 squared, which is negative 1. I cubed. Well, the easy way to do this is to say that's I squared times I, and recognize that I squared is negative 1, so I get negative I. And then I to the 4th, well, that is I squared squared, which is, again, negative 1 squared. So I get 1. And then I to the 5th, well, that's going to bring me back to I. And then I to the 6th, well, that is going to bring me back to I squared, which is negative 1. So this follows a pattern that goes in 4s, right? Y'all see that? I know something else that follows a pattern that goes in 4s. All right, let's go down here. So, let's expand some of this stuff out using these ideas over here. So, I get 1 plus it, and I get minus, because the I squared turns into a negative 1, t squared over 2 factorial, plus, this is a minus because I got an I cubed. So I get minus I cubed, minus just I, times t cubed over 3 factorial, plus, all right, I got I to the 4th. That's 1, right? So I just get t to the 4th over 4 factorial. And then, all right, I get I to the 5th. That's plus I times t to the 5th over 5 factorial. And then I get minus, because I to the 6th is negative. So minus I times t to the 6th over 6 factorial. So from here, I'm going to split this up into different parts. I got that and that. Notice all of my odd pieces have I's on them. Oh, I messed something up there, didn't I? Did you catch it? This should not be there. Why is that? It's because, it's because I to the 6 is negative 1. All right, so all of my odds, look, they've got I's on them. And look, all the odds in this are signs. And look, my Euler's formula has I's on the signs. And let's change colors. This, my evens, look at that. All of them, they don't have I's on them. So let me split them up. I'm going to write it as 1 minus t squared over 2 factorial plus t to the 4th over 4 factorial minus t to the 6th over 6 factorial. Can you guess what the next one would be? It would be plus t, and it would follow because of this pattern over here. T to the 8th over 8 factorial plus ... And now let me do the green. Yeah. All right, so here's what I'm going to do. I'm going to factor that I out. Times. All right, so I got this guy first, t. Then this guy, minus t cubed over 3 factorial. Then I got this one, plus t to the 5th over 5 factorial. What's the next one going to be? You can guess it. T to the 7th over 7 factorial. Plus ... That pattern's going to go for forever. And now look at this. Look, this. That's what I have right here. And look at this. Oops. Look at all those guys. That's what I have right here. Except for instead of t's, I got x's. So what do I get? I get that this is equal to cosine of t plus I sine of t. And look. What did we start with? We started with e to the it, and we got this. So all we did was we used some Taylor series to prove Euler's formula. And all we got to do now is throw a little a in there, and it'll work. And I've proved it to you. And I think this is the only way to prove it. Oh, my gosh. And there it is. Bam. E to the it is cosine t plus I sine t. It's always true.